Welcome back from the break, kindly sponsored by WR Grace. I hope you had time to do your one-to-one meetings or to visit the booths. Uh, this session is focused on solutions for residue upgrading. We have three presentations for you today. So first up, we have a presentation from Axence by Guillaume Cuille, he's a residue upgrading technologist. His presentation is addressing market and environmental requirements with flexi-coking. Our second presentation comes from HTE, from Florian Huber, who's a senior scientist, R&D solutions. His presentation is adding value to catalytic bottom of the barrel upgrading by advanced catalyst testing. And our final presentation of the session is from Shell Catalyst and Technologies, from Simon Cackett, who's licensing technology manager, and his presentation is titled Shell's Hycon Moving Bed Demetallization Technology. So a warm welcome to our three speakers, and please prepare your questions because we have a Q&A at the end of the session. Thank you.
So hello everyone, I am Guillaume Cuillet. I am a technologist at Axence, working of bottom of barrel technology and more and especially in flexi-coking technology. So today the objective of my presentation is to show how we can address, how Axence can address the market and the environmental requirements with flexi-coking technology. First of all, some news. Axence and ExxonMobil signed an alliance agreement to provide a flexi-coking technology and integrated resin conversion solution. This includes standalone flexi-coking technology license option in standalone or in combination with Axence HOI process. So Axence will market, license, and provide engineering work and technical support for the design, construction, and startup of a new flexi-coking unit. Flexi-coking, in fact, come in complement in our portfolio, in complement of our resid hydrotreating technology, high-val technology, of Axence resid hydrocracking technology, HOI technology, solvent desasphalting technology, Solval. And now we have in complement the fluidized cracking technology, flexi-coking technology. So why flexi-coking? Flexi-coking is there to target the zero fuel. It means that we will address both the new requirements in terms of fuel oil market and address the new requirement in terms of petcoke market. Why for the fuel oil market? Because we are going to produce no fuel market, no fuel oil. It means that we also are going to produce no bunker fuel. In fact, this solution is good as it is not subject to future IMO specification change. We see that in the past years, the emission have been more stringent and stringent on fuel oil, reaching down to 0.1 sulfur in the bunker fuel. Also, in terms of petcoke, flexi-coking is producing nearly no solid fuel, and we see that the new petcoke and it's also producing lower sulfur petcoke, and it creates less dependency for the refiner on eventual new future petcoke market evolution or any specification evolutions. So what is flexi-coking objective? The objective is simple, it's zero fuel. Zero fuel oil production while upgrading a wide range of heavy oils into valuable products. So wide range of heavy oils, it means straight run vacuum residue, unconverted oil from evaluated bed, pitch from SDA, or any kind of slop. from the refiner. The product, LPG, and the whole range of distillate from light coker gas oil to heavy coker gas oil, while producing some flexigas. What are the general principles of flexi-coking? Flexi-coking is a fluidized thermal cracking process operating at low pressure, less than 2 bar, and at high temperature, around 520 degrees C. It's a non-catalytic process, and this fluidized thermal cracking process is integrated with a gasifier. This gasifier is there to supply the energy for the process, to upgrade the coke produced inside the reactor into flexigas, and having a limited purge, generally less than 2%. The typical performance of the flexi-coking is basically a full conversion of the feedstock, up to 70% of liquid yield, according to the type of feedstock, and 3 years of cycle length. Among the key advantages, the feed flexibility, of course, can process straight run VR, unconverted oil from evaluated bed, pitch from SDA unit or slop. It's a commercially demonstrated technology with more than 40 years of experience and 3 units started up since 2012. It's also showing reduced emission compared to daily coker, as it's a closed process. If you look at the simplified scheme of a flexi-coking technology, it basically consists in 4 main sections. Let's say a reaction section, which is having the 3 main vessels of the process: the reactor, the heater, and the gasifier. And a flexigas recovery section to clean and departiculate the flexigas. The coke handling section to handle the purge and of the flexi coking technology, and the fractionation and gas plant to recover and separate in different cuts the effluents of the reactor. Among the technology capabilities of the flexi coking, it can handle up to 40% CCR. The largest operating unit is about 65 kBD, and it's demonstrated more than 95% of stream factor. The turnaround cycle up to 3 years. Now there are 13 units licensed and 7 are in operation, and less than 3% of purge. If we look at some typical performance of flexi coking on a 35,000 barrels per day of straight run vacuum resid roll, we see that we obtain around 74% of C3 plus yield and 420 megawatt of thermal energy. The breakdown of the liquid effluent is 6% LPG, 17% naphtha, 23% light flexi-coking gas oil, and 28% of heavy flexi-coking gas oil, and altogether producing around 3% of purge. The thermal energy is composed by flexi gas coming from the gasified coke of the flexi coking, and some fuel gas that is also produced in the process. What are the key advantages of the flexi coking? It is, first of all, it's commercially demonstrated. As we know, it's key when we are talking about heavy bottoms upgrading technology. There are 7 units in operation, more than 40 years of experience on this technology, and FlexiCooking has 6 new licenses since 2012. This technology show also high flexibility and demonstrate low and produce also low emission flexigas. It means that we can target the zero fuel production. It can handle a large range of feedstocks and produce also a flexigas which is having less than 10 ppm of H2S content, meaning that while burning it will produce low SOx and low NOx. It's also CAPEX and OPEX competitive because it's a low pressure carbon steel construction process. It requires no catalyst and no hydrogen, and it demonstrates a very high stream factor, more than 95%. If you look at the reference list and the FlexiCooking in the world, it's 13 licenses spread in all continents, in America, in Europe and Russia, and in Asia. The oldest unit is in Japan, operating since 1976 in Kawasaki of 24 kbd. And the latest unit in operation was started up in 2019 in Engi, in Brunei, of 19 kbd. We expect there are the largest operating unit is in Venezuela, 65 kbd, and there are two licenses in Russia, in Tuapse and in Moscow, respectively 50 kbd and 40 kbd of capacity. Two new units are expected to be started up in 2021. In Talara in Peru of 23 kbd, and in China, in Hongren, of 19 kbd. In the news, we have been this year awarded of a new reference, which is currently under design at Axens, of 36,000 barrels per day. Altogether, the total capacity of FlexiCooking technology is more than 400,000 BPSD. FlexiCooking also will bring a change in terms of utility balance. As it's a flexigas producer, this flexigas can come in substitution of fuel gas. This flexigas can be used as in various places inside the refinery, for steam production, for electricity production, and also more generally in refinery furnaces and petrochemical furnaces. And thanks to RT Petrochem, we have a unique know-how in furnace retrofitting, while implementing FlexiCooking technology inside the refinery. More generally, FlexiGas is a COH2 fuel gas base, which is having a content less than 10 ppm of H2S, and while burning, it's producing low NOx, low SOx, and low particulates. What is the position of FlexiCooking in Axens portfolio? In fact, constitute a new asset in our Axens bottom of barrel portfolio. In standalone, of course, there is a known H-oil process, which is a H2 addition technology. And now we have the FlexiCooking carbon rejection technology. And of course, it can bring a very high value, especially in combination. For instance, HOL and flexi-coking technology will bring the highest liquid yield, ideal for zero fuel solution, will limit the fuel gas production, and we can still see it as a stage investment. SDI, we can also imagine SDI and flexi-coking to upgrade the C3 pitch coming, the pitch coming from C3 SDA. And if we look more closely at the HOL and flexi-coking combination, it's showing a very high synergy, especially to target the zero fuel. It can be a smart solution to answer the new specification for IMO 2020, as we produce a very limited amount of, we are going to produce zero fuel. In terms of petcoke, we are going to have a very, we are going to produce nearly no petcoke. In terms of economics, it's showing the highest liquid yield. In terms of flexibility, it's showing, it's allowing various optimization options. And there is various use of flexigas, as shown earlier. So if we look at the typical conversion and performance of both technologies separately, HOL and flexi-coking on Arab medium. The typical conversion on this type of feedstock can be up to 93% on HOL, and we can reach a full conversion of flexi-coking. And in terms of C3 540 plus 540 yields, it's 72% for HOL and 66 for flexi-coking. And in fact, the point is to of this synergy is to gather the strength of both technology. The highest liquid yield for the high liquid yield from HOL and the zero fuel from flexi-coking. And we see that all together on the same feedstock, we can reach up to 84% of liquid yield while combining the technologies, and reduce significantly the quantity of flexigas that has to be valorized, 9 to 8% of the total feedstock. This combination accommodates very well, especially at very high capacity. This example was set at 90 kbd of straight drum vacuum residue on Arab medium. If we look at some key indicators, the HOL and flexi-coking synergy show a near full conversion of the vacuum residue, flexigas production divided by 3, and the C3, the liquid yield, let's say, boosted up to 84%. This is a clear demonstration of synergy between HOL and flexi-coking that can bring substantial value, especially at high capacity. Among the takeaway message I want to like you to remember from this presentation is that flexi-coking answers the zero fuel target. It's also answering the challenge of reliability and performance for vacuum residue process. And of course, in combination with HOL, flexi-coking and HOL show a very high synergy to reach high performance and high flexibility. Thank you very much. I'm waiting now for your question, if you have any. Thank you.
Thank you very much for the introduction, and welcome to my presentation. I will talk about advanced catalyst testing and how to add value to catalytic bottom of the barrel upgrading. Let me start with some slides on our company to give you an idea on where we actually come from. So HTE is a high throughput experimentation company, worldwide leading provider of technologies and services on enhanced catalysis R&D. We are the largest independent high throughput lab in the world with more than 50 reactor systems in-house. We are roughly more than 300 people, and we are located in Heidelberg, Germany. Here on the left, you see some of our customers. So you can see the major oil companies, catalyst vendors, chemical and petrochemical companies. What we are doing so on this slide here, we are having two main areas where we are active. That's one thing is here on the right. We build turnkey ready test systems, which we sell to our customers. And on the right side, that's the second part, what we call R&D solutions. We actually utilize our test equipment to make contract research. And the important thing here to note is if we do research programs, all the catalyst and process IP belongs to the customer. On the next slide, I just give you an idea on which applications we actually focusing on. We are active in the refining and energy area. It's typical hydroprocessing applications, naphtha conversion processes, and FCC applications. We're also active in the chemical and petrochemical area, where we have typically syngas chemistry, oxidations, hydrogenations. We are also active in the environmental catalysis, on automotive catalysis, but also on stationary emission control. And here on the right, we are also more and more active in renewables, meaning biomass conversion to biofuels and biochemicals, CO2 utilization, waste stream utilization, and also plastics recycling. Now let's come to advanced testing. In the next slides, I will give you some key features, what we think is important when we talk about advanced testing. We are here not talking about academic research, but it's really industrially relevant catalyst testing, in particular for adding value to bottom of the barrel upgrading. Everything starts here on the next slide. Everything starts with the key enabling technology. And what you see here, we typically operate in the range of 200 or several hundred grams of catalyst. And from our experience, actually, most catalyst or many catalyst tests you're doing, you don't really need a large amount of catalyst. You don't need a large pilot plant facility. We actually can do quite a lot in this scale, what is written here. We typically divide our technology or the technology into two parts. Here on the left side, it's high throughput screening. Here you typically have many reactors in parallel. You have small amounts of catalyst and you can test powder and shape material. And here everything is about multiplicity. That means you have many reactors in parallel. You can test many formulations in parallel and have a direct head-to-head comparison. On the other side, we have technology, bench scale technology, where you typically have less reactors, so lower degree of parallelization. You have larger catalyst amounts, and you typically focus on shape material. Here, everything is about flexibility, means individual operation of your catalyst systems for process optimization and also for producing larger amounts of product quantities. If we now look into a typical trickle bed test system, which is can be used for bottom of the barrel upgrading, then the really important thing is that with your system, you really can simulate industrial operation condition, meaning you are able to operate at the relevant temperatures, at the relevant pressures, relevant flow rates. So you really need to operate in the industrial window to really add value to the refinery. in addition to that, what is very important for the refinery, of course, is full mass balancing, because the refinery needs to know where the product go, what are the yields of the different products. They also need product fractionation for your test, and also detailed product analytics, because they want to know what are the key fractional properties of their different cuts. So that's about the technology. If we now come to the catalysts, typically when we talk about high throughput experimentation, or let's say traditionally, people would think it's about testing powders and model catalysts, but that's not true anymore. Nowadays, the focus on high throughput testing actually is real commercial catalyst and shapes. And if you want to add value to your customer, you really need to be able to test commercial catalysts, commercial sizes and shapes in your unit, irrespective of the scale you are using. Then you can really make a difference. The same is true for feedstocks. Again, some people think high throughput, that's model compounds. But again, over the years, high throughput really has developed into the real material. So high throughput really also needs to be able to process the real industrial feedstocks coming from the refinery. Then you make add value to your refinery. Here are some shown some examples, might be naphtha feedstocks or middle distillates, but also the heavy material or bio feedstocks, as you see here on the right side, and also very challenging Fischer-Tropsch. If you want to do industrial research, you need to be able to process these feedstocks. If you look closer into bottom of the barrel upgrading, here in the table I listed a few very typical industrial feedstocks, like the atmospheric resid feedstocks, the DAO blends, but also very heavy vacuum resid feedstocks. This vacuum resid feedstock, for example, are among the heaviest feedstocks you can get out of the refinery. And the interesting thing is all these type of feedstocks are, and nowadays state-of-the-art high throughput testing can really be processed in also small scale units and can deliver reasonable results. So realistic feedstocks, that's very important. On the next slide, we have an example on a typical residue hydrotreating application. If you look into an industrial reactor, you typically don't have only one catalyst in your reactor. You have several catalysts, a complete catalyst systems. If you look at resid, you might have a HDM catalyst with high metal capacity and moderate activity, then a transition catalyst with a lower capacity but higher activity, and then the very high active HDS function. And if you want to do testing for the refinery, you need to have a look at the complete system, investigate the whole system. And here, high throughput testing really has a benefit, because as you see down here, you can typically test many reactors in parallel here, like 16 reactors. And with these 16 reactors, you can really test different combination of this catalyst system, different stacking approaches. If you look, for example, on position 1 to 10, you see that we are simulating here a complete axial profile of these three catalysts. So you get an output at different positions in your reactor. That really adds value to the refinery, because this data can be used, for example, for a layout of a kinetic modeling. If we come back to the refining, if you look into a typically refining operation like the resid, it's multiple catalysts, but it's also typically not as it's shown here, that you put all your catalysts in one reactor. No, it's actually several catalysts are several reactors that are operated in series. And if you want to utilize high throughput experimentation, you also need to take this into account. So what we have done over the last years is like make a reactor in series operation also possible in the high throughput, meaning in the small scale testing area. On the left, for example, you see here a configuration where you have two reactors in series. Here's the first reactor connected to the second reactor, and then you have an output of the total product. However, with this reactor in series configurations, you also want to have the output from the first reactor. So what we have done is like put the third reactor. It's kind of a mirror of this first reactor, which actually generates all the output you want to have from the first. Here on the left, it's for two reactors in series. You can think the same about three reactors in series. If you take now, shown here on the right, a typical 24-fold unit where you have 16 individual heating blocks, we actually can test several systems, complete systems in parallel. If you think, for example, a two-reactor system, you can test 8 systems in parallel, 8 different combinations. If you have 3 reactors in series, you can even test 4 systems in parallel. And at the same time, you get the full interstage quantification. So that really shows you there you can really gain speed and get your data fast and have a fast catalyst selection process in this way. So that's some key features. On the next slide, I want to share with you a case study which we did with the customers, SK Innovation, South Korean refining company. Area is again residue hydrotreating, and what they wanted to know is they typically work with pilot plant scale facilities, but they wanted to know, can we actually utilize high throughput technology for our industrial research? Can we actually, as I described before, speed up the research and still have a meaningful data? So they took our technology and compared it to their pilot plant data. And the outcome, what you see down here is what they really found out is that this high throughput data produced with a small scale of catalyst and feedstock really matches the pilot plant data. So with this, I actually already at the last slide. So I hope I could show you with the slides before what are actually the key features of advanced testing and especially of high throughput testing, and how to actually add value to areas like bottom of the barrel upgrading. If we sum up here, it's like the key is, of course, a robust and flexible technology, because you are dealing with real, sometimes nasty feedstocks, commercial catalysts. Another point is, of course, if you want to gain speed, then you need to do parallel testing, head-to-head comparison. Then you have a fast response, and then you can get your data very fast. And I mean, we all know ordering a catalyst nowadays can take up to 1 year. So if you in this process can speed up your testing to get results before you start ordering, you really have a benefit there. I mentioned it before, of course, if the testing is only meaningful if you can test commercial catalysts, if you can take the real feedstock from the refinery, so the actual feedstock that are processing in the refinery, and you need to meet the operation window of the refinery. Otherwise, all your data like selectivity, yields, output, you cannot be sure that they are in the meaningful window. What I also said showed on the slide before, of course, you need proven test protocols. You need to validate them against industrial experience or pilot plant data to be sure that it's really valid what you get out, and that you can directly use it for the refinery. So in this way, I hope I could show you that high throughput testing, originally coming from a model and academic research, really has grown over the last years. We are now in this area, especially in the hydroprocessing area, for more than 10 years. And we really have seen that we have reached a level now where we actually can do industrial relevant testing. And the benefits clearly are, it's fast because you have the parallel approach. You generate high quality data, also statistics. It's cost efficient because you do not need very big pilot plant facilities with a lot of catalyst or feedstock. And what you also have seen on the last slide, it's really industrial relevant. The data that you produce are relevant for the industry. Thank you very much for your attention.
Yes, thank you for the introduction. I'm really pleased to have this opportunity to talk about Shell's moving bed technology and how it can be used to improve the performance of deasphalted oil hydrocracker or residue hydrotreating unit, and how in particular the technology can be used to allow refineries to process difficult, high metals content crudes. So this slide, I'm setting out the agenda for my presentation. I'm going to talk a little bit about typical objectives that refineries are taking to improve their competitive position. I'm going to talk about the track record of Shell's moving bed technology, both in vacuum residue, and deasphalted oil hydrocracking, to show that this technology has been successfully deployed in total for more than 30 years. Going to talk about how moving bed technology can be used to debottleneck your assets, and finally move to a case study for Shell's Pernis refinery in Rotterdam. So, as we all know, refinery margins are being squeezed at the moment with additional crude capacity becoming available, and also new conversion units being commissioned. And this is at a time when the demand for refined products is under pressure. So it is important that refineries take action to improve their net cash margin generation capacity. So many refineries are looking to increase the amount of crude flexibility that they have, either to process heavier, more difficult crudes, or to be able to process crude from different parts of the world, so they can take advantage of market price fluctuations. Also, recent changes in the IMO regulations mean that there has been a continual pressure on fuel oil demand, and many refineries are investing in projects to reduce their fuel oil production and looking to increase the amount of middle distillates that they produce. Refineries are also seeking to produce more higher value products like lubricant base oils, or for intermediates that can be used for petrochemical production. Finally, there's pressure on refineries to extend the cycle length for their process units so that they can reduce their operating costs. So Shell first commissioned its Hycon moving bed technology in 1989 in Pernis refinery in Rotterdam. The technology was incorporated in a vacuum residue hydrocracker, so-called Hycon unit, and it was designed to process vacuum residue from Maya crude. So Maya Maya vacuum residue contains approximately 250 parts per million metals. So the unit was designed with 3 moving bed reactors with a total of 7 moving beds. And the purpose of these reactors is that fresh demetallization catalyst is added on a semi-continuous basis to the top of each reactor. And this catalyst removes or allows the removal of metals from the feed. The reactors are then followed by 2 fixed bed reactors where additional Conradson carbon reduction is affected, and also the feed is converted to lighter products. Unit has consistently achieved 2-year operating cycles, processing 100% vacuum residue. Since 2018, the Shell Hycon unit has run as a deasphalted oil hydrocracker. So a solvent deasphalter was placed upstream of the unit, and now with the new feed quality, the amount of metals to the unit is up to around 95 parts per million, which means that we only retained 1 moving bed reactor, and the now 4 fixed bed reactors are there to achieve complete demetallization of the feed, removal of Conradson carbon, denitrification, and conversion. So what does the moving bed technology do? So it allows fresh demetallization catalyst to be added on a semi-continuous basis, so that you can achieve consistent high activity with no real deactivation as the cycle progresses. The rate at which the catalyst is replenished can be adjusted depending on the amount of metals in the feed. And the system includes proprietary internals, so that the feed is properly contacted with the catalyst, and there's also a system so that the catalyst can move slowly through the reactor and be removed from the bottom. If for whatever reason the catalyst has not absorbed a lot of metals, it can be recycled and reused. So moving bed technology can be a very good revamp option for an existing hydrocracker or residue desulfurization unit. So this can either be achieved by placing the reactor on the plot space of the unit to be revamped, or by building a new unit upstream of the process units. So to summarize, shell moving bed technology was started up in 1989 in vacuum residue hydrocracking mode and was revamped to deasphalted oil hydrocracking mode in 2018. So shell moving bed technology has now been in operation for more than 30 years. Since 2020, the technology and all the associated intellectual property and operating experience has become freely licensed in the market. So this plot diagram shows typical configuration for a deasphalted oil hydrocracker with shell moving bed technology, with a solvent deasphalter upstream of the unit, and here we've shown an optional gasification unit. So the moving bed technology allows a higher extraction depth in the solvent deasphalter, which means that the process will produce more mineral distillates. It also produce more high quality unconverted oil that can be used as a petrochemical feedstock or for heavy base oil manufacture, and it reduces the amount of pitch and therefore the amount of fuel that's produced. Next slide shows how, some numbers, and these numbers are for a typical heavy crude from Arabian Gulf feed. So for a deasphalted oil hydrocracker, the metals need to be limited to around 35 parts per million if you want to achieve a 2-year design cycle. By adding one additional moving bed reactor, the amount of metals in the feed can be increased conservatively to 95 parts per million. And this enables a higher deasphalted oil yield. And for this example, the DAO yield can be increased from the high 50s to the high 70%. And this obviously has a significant positive impact on the project economics. Here we've got a block flow scheme for a moving bed reactor in a residue desulfurization unit upstream of a residue FCC. So because there's a moving bed reactor, the amount of metals in the feed can be increased. And this enables the refinery to process more difficult crudes, or allows more vacuum residue to be included in the feed diet for the residue unit. So this gives a better yield of higher value products and improves the economics of the unit. So now we're moving to the case study. So this is Pernis Refinery, and the diagrams here show the original fuel system and what happened after the revamp that was started up in 2018. So originally, there were 2 units that were running on 100% vacuum residue. There was the Hycon unit, and there was a gasifier, which was commissioned in 1997. And you can see here that the HyCon unit still makes, it's processing 100% vacuum residue, but it still makes a considerable volume of fuel oil. It's around 35% of the product is fuel oil. In the new situation, there's a new solvent de-ash-filter installed, and the HyCon unit has been converted to a DAO hydrocracker, and the gasifier has been revamped, so now it can accept asphalt from the solvent de-ash-filter. From the solvent de-ash-filter, the gasifier now is capable of processing this higher viscosity feed. So the revamp actually required an investment of around $500 million, which was significantly cheaper than the alternative options that we looked at the time. The DAO hydrocracker is now designed to allow the refinery to process large quantities of crude from different supply regions. So it can process 100% Urals or Arab Light or West African crude. The feed CCR for the unit can be as high as 8.7% weight, and you can process more than 50 parts per million of metals in the unit. The unit produces high quality distillates so that that can be directly blended into either the jet or the Euro 5 pools. The unconverted oil is fed directly to a VGO hydrocracker. In summary, the unit has now achieved a 2-year operating cycle, operating at 75% conversion to diesel and lighter. It has enabled the refinery a significant increase in crude flexibility. It has reduced the amount of fuel oil that the refinery produces by 35%, with a corresponding increase in middle distillate yield. So now coming to my final slide and my kind of key takeaways from my presentation. I just wanted to say that Shell Moving Bed technology has a proven track record. It's provided Pernis Refinery the ability to run high metals content crudes for more than 30 years. The technology is now available for licensing for the first time because we recognize that reducing fuel production, increasing crude flexibility is a margin driver that applies to many refineries around the world. A solution, a residue reduction solution, including the solvent de-ash filter and a DAO hydrocracker with moving bed technology, is a realistic option, that requires moderate capex for many refineries around the world. And I'm just hoping that this presentation, gives people some food for thought. Thank you very much.